Alright, so we're going to start this lesson today is we're going to start way back in the year 1895. And so the reason why I've picked the year 1895 is that this year kind of starts a set of a decade where the world of physics really got rocked and turned on its head. And so if we look at the things we know in 1895, we know that all matter is made of indivisible particles that we call atoms. We have an idea of different elements. We have the periodic table really starting to get formed and filled in. Some things we want to know is what are some new elements, what are their masses, how do they fit in the periodic table, does the periodic table actually work, is kind of one of the pieces of information we want to know. And the other question when we talk about matter being made of indivisible particles called atoms is how does gravity really work? We know that matter is attracted to other matter by this force we call gravity. We're not really sure how that force really works. It doesn't seem to make sense in the context of other things that we know. The second thing that we know is that light is a wave of alternating electric and magnetic fields. And we'll get to that later on this term when we start looking at Maxwell's equations. By the mid to late 1800s, we have a model of electricity and magnetism where electric fields and magnetic fields are related to one another, and this alternating electric and magnetic fields is what we call electromagnetic radiation, and light is one of those types of radiation. We know light's a wave because it's these fields that oscillate in wave-like patterns. We also know lots of other things about light being a wave. We know it reflects, we know it refracts, we know it does diffraction, we know it does interference, all the things we normally think of as wave-like properties. So the only thing we really need to know here is, can we measure the speed of light a little more specifically? The third thing that we know in 1895 is that, well, obviously light travels through a vacuum. If light is a wave, there must be a medium that light travels through, and so this medium is what we call the ether. So there's some things about the ether that are interesting. The first thing is that it must be massless, because we know it doesn't influence gravity. We know it must have very low viscosity, because we know it doesn't change the speed of the Earth in its orbit. And we know it must be pretty hard to detect, because, well, we've never actually seen it before. So the question is, can we detect the ether and prove that this idea, or demonstrate that this idea is true? So I picked these three because these are three kind of pillars of what the world is like in 1895. And really, what we're looking at in physics is we've got a few more questions to answer, but we pretty much figured everything out is the idea at this point. So in steps this guy by the name of J.J. Thomson, and he starts to do some experiments with matter, particularly what are called cathode rays. We figured out is that cathode rays, when you put a high voltage across either a gas or a metal, you get this beam of light that comes off of it that we call a cathode ray. The first thing he discovers about cathode rays is that they're negatively charged, and so he wants to try to figure out what are these cathode rays really doing? Are they some sort of light? And if so, how is light negatively charged? And then where does this negative charge come from? Like, that doesn't seem to make any sense in his head. So he devises an experiment that looks like this. What he has is he creates what I call a cathode ray gun. How it essentially works is you have a filament here that you're going to heat up to a really high temperature. What that happens to do is boil off electrons off of the filament, and then you're going to put on the cathode a negative charge and on what we call the anode a positive charge, and you're basically going to accelerate these cathodes across this potential difference. That's why I call it a gun. It kind of acts like a gun. You're shooting a beam of cathodes out of here. Well, what he's done in this experiment is he's taken a pair of metal plates and basically created a little capacitor in here where he has a positive charge and a negative charge. There's a constant electric field between those plates. If you turn those plates on, he determines, well, I can get these things to bend as if they were negative charges. Cool. The second thing he does is he has a pair of electromagnets. And so what he does after he turns on the magnetic plates, he turns on the electromagnets and tries to bend the beams so that it goes in a straight path. So let's get a look at what he's doing in this experiment. So the first thing is he shoots this beam of electrons at some speed Vx that we don't know, and they encounter this constant electric field that we can calculate because we know the potential difference across the plates, and we know the distance across the plates, and we know in a parallel plate capacitor the electric field is constant. I also know the length across these plates, which is important to know, and I can measure on that end how far wide does this thing actually get bent or deflected. So if we start to actually do some math, we can say F equals ma for inside the plates. I know F should be equal to E times Q because force or electric field is force on the charge divided by charge, right? And so I can actually get this ratio for Q over M, mass per unit of charge, by looking at the acceleration in the electric field. So how do I find the acceleration? Well, that's simple. I could use two-dimensional kinematics. Initially, before this object starts in here, it has, well, an acceleration of, well, 0, and as it gets bent down, we get this type of acceleration. Well, we could figure out what v or what t is by using this equation. That I know that the length, vx times t, I know there's no acceleration in that direction, and so we get length divided by vx equals t. I can plug that in for y and plug in what I know about acceleration, and then I get an expression for how y depends upon the electric field, the charge, the mass, the vx, and the L. Now the question is, can we figure out this vx? Because we don't really know what the v is. The things that I would need to know in order to calculate the v from the potential difference would be what is the charge of a cathode and what is the mass of a cathode. So what I do next is I apply the magnetic field. The magnetic field bends the electrons so that they move in a straight path. We could use electric force is equal to magnetic force, and so this velocity should be equal to electric field divided by magnetic field at this point. So if I plug that result in for velocity, I get an equation like this where I could calculate the deflection of the beam by using this equation here. Now, what Thomson did was he went one step further and he said these are things that all I can measure, so what I can determine is what the charge to mass ratio of an electron is by using other pieces of information like how much it accelerated across my electron gun. I can maybe figure out what both the charge and the mass of this particle looks like. And what he determined, or what his claim was, is that these particles had a mass that was 1,000 times smaller than the hydrogen atom. Since the hydrogen atom is the smallest known atom at the time, and really the smallest known atom of any element, and these things are 1,000 times less massive, that means there must be a particle that's smaller than an atom that's coming from an atom. If you actually do this experiment and do a more precise measurement, you find that the mass is actually closer to about 1,800 times smaller. So Thomson was in the right order of magnitude, but he's about 50% off, give or take 10 or 15%. So he called these particles electrons, and so this kind of throws a wrench in the whole works, because now we know there's a particle smaller than an atom that has to come from an atom that has a certain mass and a certain charge. It happens to work out that his charge to mass ratio agrees with other experiments that were being done on charged particles at the same time, like the Millikan oil drop experiment. He starts to see the same ratios of charge and mass showing up. So we'll actually do in class the charge to mass ratio experiment for an electron. I do a slightly modified version because my apparatus is different, and we'll discuss how my apparatus is different from the one Thomson used when we get to class. I actually believe the apparatus that we use is probably more precise and gives us better results than what Thomson had available to him at the time. And so our goal of this experiment will be to determine the charge to mass ratio of an electron, and historically, this experiment has worked very, very, very well. I think the last time I did this with my AP Physics class, we got a charge to mass ratio as a group that was something like within 0.25% of the accepted value, like right on. And that's fairly normal for this particular experiment. So let's jump ahead 10 years to 1905 and figure out, well, what happened during these 10 years that really messed things up. So the things we know, all matter is made of indivisible particles called atoms. Well, no. They're particles smaller than an atom, electrons. So that means our whole model of what an atom is has to change. And then we have to figure out, well, what model of an atom actually matches what we see in nature. So there's a whole host of more experiments that have to happen to figure out what really is an atom. And then the second question is, are there other particles smaller than atoms? And you would obviously say yes, protons and neutrons, because they make up atoms, but they're not the only ones. We start to see there's a whole host of particles that are smaller than atoms. Well, some larger than some types of atoms. And so that opens up the door to a whole set of physics called particle physics. What's actually going on here? So matter is made of atoms. Pretty simple view of matter. Matter's made of all of these smaller particles that make up atoms. Oh my God, what's going on here? So that's basically what J.J. Thomson happened. It works out that J.J. Thomson won a Nobel Prize for this experiment. The second one, light is a wave of alternating electric and magnetic fields. Well, that seems to be pretty safe until Einstein shines some beams of monochromatic light on pieces of metal and gets cathodes to get ejected from them, electrons. What that means is that there has to be a collision from light and this electron in order to get the electron, a particle, to come off of this. That's a problem if light's a wave because, well, what is the particle that's actually interacting? So this experiment, what we call the photoelectric effect, basically demonstrate that light is made of particles because light can undergo collisions, and collisions are a particle property. So the question that kind of comes out of here is, how can something both be a wave and a particle? At this point, light's the only thing that we think of that could be both a wave and a particle, but as we start to delve deeper into other particles like electrons and protons and neutrons, we start to see is there other particles that behave as waves and particles as well. And so we open up this whole door to this field, quantum mechanics, of what's actually going on with waves and particles. And so the third piece of information that we thought we knew in 1895, light travels through the ether. Well, there's an experiment called the Michelson-Morley experiment. Basically what they did is they sent a beam of light on a long path going north-south, a beam of light on a long path going east to west, and they tried to see what type of interference pattern happened between those two beams. Well, if light travels through the ether and the Earth is moving through the ether, we should see something that looks like the Doppler effect happening on at least one of those two paths. Well, we don't see that. They actually conducted the experiment, I don't know, 15, 20 times. They had other people conduct the experiment. This experiment has been done hundreds of times, and we've never found the ether. So the question then is, how can light travel through nothing? Well, if light's a particle, that maybe starts to answer that question, but well, maybe it's a little more complex than that. Now, the one question we had in 1895 that really still endures in 1905, and I would argue still endures today, is how does gravity work? There may be some ideas of maybe how gravity really works, but we don't really have a solid foundation of what gravity really is and how it fits in the whole picture of what other things exist. The problem with gravity is if you start looking at it from like a macroscopic view, stars and galaxies, we have a pretty good idea how that works. But that view starts to break down when you start to look at like atoms. If we look at atoms, we maybe have an argument of how it works on the scale of atoms, but that idea breaks down when you get to the scale of galaxies and stars. So if you're really interested in kind of the cutting edge research, how does gravity work is a question to kind of look at and begin to try to figure out the answer to. So the reason why I say these 10 years are 10 years that really shook the foundation of, well, science in general, is we had three things that we thought we know for certain that are not true. And it opens up the door to really 3 or 4 whole new fields of chemistry and physics of how do we begin to describe what we now figured out. If we start to look at between 1905 and maybe the 1950s, 1960s, you see a whole ton of experiments that happen in both physics and chemistry that really shape what our modern view of the universe and the world is. So that's kind of my quick overview of the discovery of the electron. I like to talk about that because it is one of those discoveries that is a big deal in terms of science. It's worth pointing out those three experiments, the photoelectric effect, Michelson-Morley, and discovery of electron. All three of those are Nobel Prize winning experiments, things that really advanced science forward during their time periods.